Welcome back. We have been talking about design for quality using robustness techniques. Under the umbrella of this topic, we have spoken about design of experiments, specifically Taguchi's orthogonal array. So far, we have discussed the idea of robustness, how minimizing variance or standard deviation is equivalent to achieving better robustness, which eventually translates into better quality. Very recently, we saw how one might want to design experiments to obtain the responses such that the standard deviation can be quantified or the variance or the spread of the data can be quantified. One of the widely used techniques, more from a manufacturing data perspective or manufacturing examples perspective, is the Taguchi's orthogonal array. We have already looked at the history of that. The important takeaway that you need to remember about the Taguchi's orthogonal array is the way in which the data is balanced. There is no bias with respect to a particular level. Within a column, the levels are balanced, and between any two column also the levels are balanced, but that was not the case in one factor at a time or all factor at a time kind of design of experiments. So, unless we have any kind of an information to bias a particular level, we should not be doing it, and orthogonal array inherently does not build such kind of a bias. Hence, that is one of the major advantages of orthogonal array. For today, what we will try to do for this lecture, what we will try to do is this: we will run through a example that would have used orthogonal array to generate, or it would have used one kind of an orthogonal array and responses are generated. We will see how to analyze those responses. En route, what we will do is we will worry about how to select an orthogonal array, which is also one of the important scope for this course. How to select a proper orthogonal array, because the scope of this course does not include how to build an orthogonal array. How to build an orthogonal array is more of a computer science or a math department course. Here we are only going to use orthogonal array. In order to use, we need to know how to select an orthogonal array, which is again governed by the budget or the time or the number of experiments that you can do. So, we will start with this experiment, and en route you will learn those ideas. So, currently we are looking at a plastic molding experiment, more like an injection molding, let us say, and this L8 refers to 8 experiment. We have already stated that L stands for Latin square. So, when you are talking about tensile strength as a material property, we would like to select a material that will have a better tensile strength, right. So, what do you think is the quality characteristic in this particular case? It will be larger the better, L type. But let us assume that the tensile strength, the factors that affect the tensile strength, that has been found out to be temperature, pressure, time and additive. There are 2 levels to it. For each of the factor, there are 2 levels and some values are given, okay. 200 degree, 220 degree, time 30 minutes and 40 minutes. 0 represents the initial level and 1 represents level 1. So, in this particular case, what they are talking about is there are 6 combinations. In what sense? If you have 4 factors A, B, C and D, what have we seen? The single factor, the main factor is A, B, C and D. The 2 factors are AB, AC, AD, BC, BD and CD. Then the 3 factors are ABC, ABD, BCD, and one 4 factor combination is ABCD. So, if you look at it, 4 plus 6 10 plus 3 13 plus 1 14. So, primarily if I have to account for all the interactions, there are about 14 of them, but we are pretending here. In principle, if you do a full factorial analysis, then you will be able to account for all these things, but in order to account for all these things, we need to do more number of experiments. In order to reduce the number of experiments, that is what Taguchi's orthogonal array proposes, you will get most of the information, but you can save in terms of experiments by at least a percent of 50 or around that. So, what they are saying is there are 6 combinations in 2 factor interaction. They are not even worried about the higher factor interaction, they are only talking about the 2 factor interactions. They are saying there are about 6 combinations, but our interest is only in the AB. This is some additional information that is available, otherwise we cannot make such kind of a decision. What are they saying? These factors are not important. Some expert comes and tells you that only A cross B is important. In such a case, you need to design a orthogonal array, sorry, not even design, you just need to select an orthogonal array to run the experiments. So, if you want to capture A, B, C, D individually and A, B together, then we are looking at what number of experiments or L. Okay. So, primarily we need only 5 columns, because there are only 5 factors that we are interested in terms of combination and main factors, right. So, can we do an L5? If it is available, we can do, but even before that, if you need 5 columns, then what should be your L? It should actually be L6, because for L6 there will be 5 columns. Please remember, 6 is the number of experiments and the columns are your factors. So, but L6 does not exist, that we know. So, the next possible stuff that you can think of is L8. Please remember, this number comes from the fact it is 2 levels raised to 3 factors kind of stuff, okay. That is a full factorial, but in our case if you take 2 level raised to 4 factors, because we have 4 factors. So, that will lead to 16. So, L16 will be an appropriate experiment, but 16 means you can cover all of these guys, but that is not what we are looking at. We are only looking at half fractional factorial. That will be L8 for me. So, we are going to look at L8. Okay. So, this is a generic orthogonal array for an L8. It does not matter what example you are looking at. You can use this array is fixed. We do not have to do any research, it has already been done. Okay. So, let us say that you are using this orthogonal array in computer science, in mechanical, in aerospace, does not matter. This combination of the levels still remains the same. Within a particular discipline, whether you are looking at a micro level problem or macro level problem, you are looking at a structures problem, you are looking at does not matter. These numbers remain the same. Then what does change? What is your output response? What are your column assignments? Those are the ones that will change. That is where the designer comes into picture. These are all already done for you. So, this is L8. So, there will be 8 experiments and there will be 7 columns which are factor. One of the important things that we will see for today is how to assign the factors in this. So, there are 2 things. One is, even if it is a 2 raised to 3, meaning 2 levels 3 factors, just ABC, how will you assign A, B, C to this? Can I just assign A, B, C, A, B, A, C, B, C and A, B, C? Is it like that, or is there some other way of doing it? Actually, there are specific focused ways of looking at it. Those are called the linear graphs or triangular tables. So, where do I go and get this L8 and this linear graphs and triangular tables? So, people have already done these kind of work, but what you just need to do is this: if you go to the back of any book that we have prescribed in, so this is Fortke's book on robust design. So, if you go to that, you can very clearly see, that there is a orthogonal array. For instance, L4, in the bracket it says for what conditions? 2 raised to 3, meaning 2 levels, 3 factors, but L4 means I cannot account for the interaction. So, you can see there are 3 columns and this is how it is done. How do I assign the factors to the column? So, one way to look at it is something called the linear graph. So, what it says is 1, 2 and 3, this is standard. What you just need to do is this: in this case there are 3 factors, right. There are 3 factors. So, I could say A, B. If I say A goes to column 1, B goes to column 2, that is what I have written here. Okay. Then column 3 should be A cross B. But we are looking at 3 factors. In that case, for any kind of an orthogonal array, there is a combination that you can write it like this. It is understood: A, B, C. You are only looking at the main factors. So, you can also have A, B and C, or you can choose to have A, B, A cross B. Okay. So, this is 2 factors, 2 levels, it is a full factorial experiment. If I am just going to assign A, B and C independently, then it is a half factorial experiment of a 3 factor experiment, 3 factor with 2 levels. So, originally you need to do 8 experiments, but L4 is only half of those experiments, half of that. So, we just saw for a general L4, if you do this A, B, then 3 could be A cross B, or you can have A, B and C. In a similar fashion, let us see for L8 how you can do this. Okay. So, you do not have to take A to be in 1, I can say C is in column 1, then B is in column 2. Then what happens? Automatically column 3 will be C cross B. Then let us say that you take D in column 4, then C cross D is fixed, B cross D is fixed. So, 2 factor interactions with 3 factors gives you 6. Then this one could be my A. So, this is one possibility for an L8, meaning 1, 2, 3, 4, 5, 6, 7. So, L8 means 7 columns. So, 7 factors is something that I can account for. This is one way. There is another way, which is this linear graph. So, in this it is slightly different. Let us say for whatever reason someone came and told you that interactions of C are very important. Then I will say C A for this guy, B and C. So, each node I am assigning a single factor and the link will give me my interactions A cross C, sorry, C cross B, this should have been D, C cross D. But you should also appreciate the fact that it is biased towards the C interactions. That information you need to have, otherwise you cannot use this one. So, the way that we have written here is, if you give A, B, C and D, then A cross B, then A cross C, then A cross D. These are the combinations and the single factors that will come into picture. So, now if you go back to the book, basically for any of the array that you are talking about, the whether it is L8 or L4 or L16 or L32, whatever you are talking about, you will have such linear graphs. Okay. So, they are even talking about an L16 array for 15 factors. Okay. That is the maximum that you can use, but you can use less. So, the point is, what happens is this your linear graphs become slightly complicated as your number of factors and their interactions increases. So, you can see here just for 15 it becomes slightly confusing. Okay. We will quickly see in this. So, let us say that you do A here, B here, C, D, E. So, A cross B will be in this one as expected, then A cross C will be in 5, then A cross D, then A cross E, then B cross E. So, you can keep doing this, right. So, this becomes slightly complex as the number of dimensions increases. So, this is like a similar biased estimate. So, if you take A here, you will get all the interactions with respect to A, but you will not get an interaction with respect to, let us say, sorry, C and D you will not get, B and D you will not get, but with respect to A, AB, AC, AD and whatever factors you have until then you can have, or there could be an interaction like this, there is only interaction between AB, CD, E, F. So, in such a case you will have to have this information that these are the factors that are important and these are the interactions that I am interested in. Okay. If you have that, so there are multiple combinations of linear graphs. Okay. On the other hand, there is also something called a triangular table, which provides similar information, but it is easier to use for a larger factor case. So, this is how a linear table looks, a triangular table looks like. So, what it says is, it gives you column numbers, okay, and what it says is, now you assign factors on one of these columns. So, if you say A for column 1, then let us say you are saying B for column 2, then what it says is, on column 3 it should be A cross B, that is all. So, for instance, if you took A in column 1 and you took C, it cannot be in the same problem, it is a different problem. Okay. C in column 3, then your column 2 should be A cross C. Okay. So, yeah, so this is the same thing that is explained in this part. Now, this is for an L8 condition. So, this might sound a little confusing to begin with, but we will start. So, as I pointed out, so it is 2 raised to 4 case it should be. okay, then only we can take a half factorial. Or if you even take let us start with 2 raised to 3. So, it is a full factorial, but we will see how the columns are assigned. Let me take A for column 1. So, obviously column 1 is A. Now, if I assign B for column 2, then what this one says, if you come from here to here, then A cross B will be in column 3. Since column 3 is already decided here, we should just say A cross B, and my next column would be, my next factor assignment would be C. So, if I take C here, A is in column 1, A is in column 1 and C is in column 4. So, column 5 will be A cross C. In a similar fashion, if I take B column 2 and I come here, C is in column 4. So, it will be B cross C. There is also another way of looking at it, but this is not the correct way though, but it will work out if you look at it. A is in column 1, B is in column 2. So, kind of A cross B is 1 plus 2. So, A is in column 1, C is in column 4. So, 1 plus 4 is 5. So, A cross C will be in 5. Similarly, B is in 2, C is in 4, 2 plus 4 is 6, B cross C will be in 6. That is one way of looking at it. Okay. So, like this if you do, so this will be A cross B, this will be C. Now, we know our these guys are A cross C and B cross C. Then you do not have a choice but to say your final D will be in. So, you can see in this. So, A cross B, A cross C, B cross C. So, all the 2 factor interactions you have got. So, this this is only if you have a 4th parameter, otherwise this will be A cross B cross C. We saw this will be A cross C and this will be B cross C. Got it, right? Yeah. So, this is triangular table also gives you the same idea, but it is easier when a large number of factors are involved.